Our next talk is going to be by Thomas Graf of Noiro Networks and Justin Pettit from VMware. Welcome. Please come and speak.
Thanks a lot, Ben. My name is Thomas Graf. I work for Noiro Networks. It's a Cisco project. I think Justin's going to start.
Yep. All right, and I'm Justin Pettit. I work for Nicira/VMware. Okay. So what Thomas and I are going to talk about is adding stateful services to OVS, in particular connection tracking that can be used to implement a firewall and NAT. So we'll start off with talking about connection tracking, then Thomas will go into NAT and then integration with other stateful services. And then the talk after this will be from Frank from Cosmos, and he's going to be discussing integrating DPI. So first I wanted to just mention that we had a performance problem with OVS. So OVS has always had good performance if you had steady rate traffic. So it could easily saturate 10 gig link. We were multi-threaded in the kernel, so flows that were established had no problems with performance. But there were certain traffic patterns which we didn't notice immediately that could cause problems for OVS. So if you had a large number of connections that were being created quickly, then the performance fell apart. Because what would happen is that we had this kernel module, which was a cache of recently seen flows. And when a new packet came in, this is an exact match cache, and when a new packet came in, or a new flow definition, it would miss and it would be sent up to user space. User space was single-threaded, and it just didn't have the performance to process those packets, or to set up connections quickly. And so, so there were applications like some peer-to-peer apps that created lots of short-lived flows, or if someone did a port scan, it would end up bringing down the performance of OVS. So for the past couple of years, that's what we've been focused on primarily, at least the group that I work in. And so what we looked at was how to improve the performance of connection setup. That was our biggest goal. And we think that we did a good job on that. We're actually feeling pretty confident about the performance now. So we did things like added mega flows, which are wildcard entries in the kernel. We made the user space multi-threaded, and then we made improvements to the classifier, which is what takes the OpenFlow rules and translates them into those those cache entries that are no longer exact match necessarily. And so last week we posted on Network Heresy, which is Martin Casado's blog, a post about what we did and about the performance numbers that we're seeing. So I'd encourage you to look at that if you're at all interested. So if you go to Network Heresy, if you do a Google search, it'll be the first blog post on that, the top one. So now that we're feeling good about performance, we want to make sure that anything that we add to OVS doesn't affect the performance in a negative way. And so you'll see that the approach that we're taking for adding these stateful services takes that into consideration. So OVS has traditionally only supported stateless matches. So a packet comes in and we only can affect what is currently in that packet. So we look at the headers and then we make decisions based on the OpenFlow description that says if it, based on these headers, this is the policy that you want to implement. And so we couldn't do something really stateful in any sort of way that had any kind of good performance. So if you had wanted to implement a firewall, there are basically two approaches that you could take. The first is that you could match on the TCP flags. So what you would do is you would enforce the policy on the SYN packets, and then you would allow all ACK or reset packets. And this worked pretty well in terms of performance because those entries could be cached and kept in the kernel. So you didn't have to do lots of misses up to user space. But the problem is that it's really not that secure because you're allowing any sort of packet that has an ACK or a reset through, which isn't great security. There are attacks that can be done through that. You can probe to see what services are available. And it also only works for TCP. So it's not great, but it worked and it had reasonable performance. The alternative was that OVS supports this learn action, which allows inserting new OpenFlow rules up in user space. And the way this would work is that when a packet came in, a new flow, then it would be sent up to user space, and then user space would use this learn action to create the reverse of the 5 tuple, inserting a new flow into that open flow table. And then when the traffic came back in the reverse direction, now there would be a rule that would allow the traffic, and otherwise you drop it. But the problem, as I mentioned earlier with this, with megaflows, that megaflows is looking to address, is that we're trying to keep things in the kernel as much as possible. So this just destroyed performance of flow setups. And so it was orders of magnitude slower than using, than if you just had an existing connection. And then neither of these supports related flows. So if you can imagine, if you have a FTP session, you have the FTP control channel, and then it generates new flow entries that are for the data channels, there was no way in order to detect that and to punch holes for those other rules. And it also doesn't do anything with TCP window enforcement to make sure that you don't have overlapping fragments or segments. So our proposal is to use the connection tracking module in Linux. And so right now we're focused on Linux, but we have plans for how we'll support this for other hypervisors as well. So the thing to keep in mind about the connection tracker is that's all it is it's just used to track the flows. There's no enforcement of the policy. So if you're using IP tables is something that's separate from contract. But if you want to keep policies based on whether flows have been established or not, or related flows, then IP tables makes use of contract. And so that's what we're looking to do, is to use that contract module. And so, and contract supports ALGs, which allow you to punch those holes for related data channels. We think that doing this at the edge makes a lot of sense. So as opposed to driving everything through a central server, you can do it at the edge. You can use those CPU cycles that are available at the edge. And that'll have better performance, and it also has better visibility because we're closer to the source of traffic, so that your policies can be better defined and more correct. And the way that we look to do this is that we're introducing a new contract action that's available as an OpenFlow extension. And then now you can match on the state bits that are returned from that connection. So this is how this is a diagram, if you use the connection tracker, about what it looks like. So a packet comes in at 1, so it comes into the OVS flow table. And if you want to do connection tracking, you call the new contract action, which sends it up to this yellow box. And so this yellow box is the existing Linux connection tracker. We haven't made any changes. So the packets, you'll send all of the packets through this yellow box, the connection tracker. And then the connection tracker has all the regular contract utilities work because it's using it's the existing tools, and so you can see from user space what flows are available. So once it goes into the connection tracker, there's this red box, which is the connection tracking table. It keeps track of the flows. It enforces the TCP window segment, or the TCP window sizes. And then it makes available to the OVS flow table now what the connection state is. So if it's a new flow, if it's established flow, or if it's a related flow. And so with OVS now, we've sent the packet through the connection tracker, and you can optionally now recirculate the packet back to OVS, now with those connection bits set. And so you can enforce the policy. And I have an example that might make it a little bit clearer. So what we're looking to do here is we want to allow any traffic. This is a very simple firewall, but just to illustrate the point. So the policy that we're looking to implement here is that port 1 is allowed to send any traffic that it wants. And port 2 cannot create new flows to port 1. It can only respond back to existing flows that were initiated by port 1. So this first rule says, if it came in on port 1 and it's TCP, and then the connection state, it's a little hard to see, but it says minus tracked. If it hasn't been tracked yet, then what we're going to do is we're going to send it to contract with zone 10, which I'll get into in the next slide, and then do normal processing, so normal L2 processing. So we're not looking, because we're allowing any traffic from port 1, we don't actually, we're not going to look at this packet again. We're just going to say forward it out to the other side. Now, if traffic comes in on port 2, it's TCP, and then it's not tracked, then we'll send it to the contract, and we'll use the same zone that was used in the previous flow. And this time we'll say recirculate. So there's no forwarding action. We're not saying what we're going to do with this packet. We're just saying bring it back to the OVS flow table. And so in the third rule here, now at this point we don't have, it's the import 2, it's TCP, and you probably would say plus tracked here, but just for just to make it a little bit smaller, we didn't list that. But and it's in the established state, then we'll allow it. So we're allowing traffic that came in that was created by that first flow that came in from port 1. And if it's in the new state, this last rule, then we drop the packet. And so this is how you could implement a firewall using the connection tracker. And there's actually a flow that's missing here which says if it's not TCP, then just do normal processing because you need to allow things like ARP. But anyway, but this is just to show how you'd use it. Yes? This one? This one? Here,
the input port 2 connection state, TCP connection state minus track.
So, sorry, I didn't hear.
Could you explain that second step in the match?
This one?
Yeah.
Okay. So what we're saying is these two rules look basically the same, which is that one is coming from port 1. The only difference is that one's coming from port 1 and the other one's coming from port 2. So traffic that's coming in from port 2, if it's TCP and it hasn't gone through the connection tracker, then it's going to match. So it's really, let me go back a slide. So the first time, so when the packet comes in, it will come here, and it won't have the tracked bit set in the connection state because we haven't sent it this way yet. So the packet comes in, and then it's not tracked, so we send it up to the connection tracker, and then I had that recirc flag set, which means that the packet will now come back to the OVS table, and now this time those bits related to the con state are matched. And so now we can implement, that's what the third and fourth rules are for. Does that make sense? Okay, great. And so I had mentioned this connection tracking zones. And so what the zones are, they allow overlapping addresses between different systems, or it allows, so for things like network virtualization, you want to, if you have two different tenants, they could have overlapping addresses. And this allows you to scope those addresses. So in the previous example, we used zone 10. And so that means that, if you have traffic that's going back and forth, they need to be in the same zone. But it allows you, if you had lots of tenants, each of those could be in a different zone. And on Linux, it's a 16-bit number, so you have roughly 64K different zones that allow overlapping addresses. And so you can just specify those as arguments to the contract action. So we started doing some preliminary numbers of this. And so on the left is the performance numbers with Open vSwitch, on the right is the Linux bridge. And so what we did was we ran a single TCP connection through the system, and it's a 16-core, 2 gigahertz system. And since, regardless of what rules we set, we were able to pass 10 gigs, regardless if it was the OVS or bridge. And so what we did was, since the number of the throughput didn't change, we needed to look for something else. And so what we looked at was the number of gigacycles per second that were used to process that traffic. So you can see with OVS in the red line, the red bar is just showing pure forwarding. So there's no firewall rules in either OVS. We're not using the con mark or the contract, and on the bridge we're not using IP tables. And so you can see that OVS's performance is slightly better than the bridge, but not significantly. Now, if we start using, if we use a firewall rule, we had one firewall rule, so that means that in OVS we're using the contract now, and on the bridge we're using IP tables. You can see that we're using a bit more CPU cycles for both, but OVS's is a little bit more of a hit because now we're redirecting traffic back through that extra module, and then we're recirculating again. But with the yellow line, now we've added 100 rules, and you can see that the performance is the performance difference between 1 and 100 rules starts to grow a bit more as we use IP tables. And with the green bar, now we've hit 1,000 rules, and you can see that the performance is, that the performance of IP tables ends up slowing down a lot more than OVS. And that's because of the architecture of IP tables versus OVS. And in OVS, we're doing flow caching that allows us to, so we don't have a linear search where we're trying to find what rule matches. We already did all of that when the packet was set up in user space, and now we push down, now that all of those packets now are hitting that cache entry. And so these are very preliminary numbers. We'll be testing this in all sorts of different ways. But the performance team over the weekend ran some numbers just to see those. Why don't we do it, just since it's being recorded, then we can.
Quick question. What's the average packet size for the 10 gig that you're...
So in this case, it was a HTTP test, so I think it just ended up using the full MTU. So these were 1,500 byte packets, I believe, unless they were using jumbo frames.
Okay. Does this time include the device I/O, or you're talking to a virtual port, or what?
So I think it does. Sorry, I'm trying to see where Vasmi is.
I'll tell you why I'm asking, because
Okay.
when you're using contract, you're recirculating every packet, I suppose.
Sorry?
When you're using contract, you're recirculating every packet.
Yes.
So you're doing 2 passes through the switch, yet the difference between recirculation and not recirculation seems very small compared to the absolute value.
Right.
That's why I was asking.
Okay. Oh, there's another question. Here, if we can do that, Mike, just so that people online can hear.
So when you recirculate a packet, is it recirculating every packet of the flows or just a few packets in the beginning when you're doing it?
So in this flow, what we're saying is that any packet that goes through, that comes in on port 2, we're going to recirculate it. We don't do it with any of the packets, just for this one, that came in on port 1. And we have to do it for every packet with the flow because we don't have, unless we pass it through the connection tracker, we don't know what the state of that flow is. So anything that you want to, any enforcement that you want to do, it has to go through the connection tracker again, because that's the only way that we know the state of that flow.
Okay, so the next question is whether the size of packet matters. You have like a big packets or a smaller packets in terms of performance, because you're going to recirculate a packet.
Yeah, I mean, I would imagine that I don't think that the performance, like OVS versus Linux, I don't think that performance would matter, but I think that the rate of the throughput would drop. We'll start getting those numbers to see what they are, but I don't know off the top of my head what I think actually maybe in the DPDK slides, they'll probably go into how many packets per second that for minimum size packets versus maximum size packets that can be handled. But I wouldn't expect any difference between IP tables and OVS. I just think there would be an overall drop in the forwarding throughput for running through Linux. Sorry.
So I have a question on the recirculation again. So from the code, every time contract is called, the API from the kernel, doesn't the SKB come back marked with the state? So it's not clear where recirculation is once it's already in the kernel data path. So
normally what happens is that when OVS is processing the flow, it wouldn't go through the connection tracker. So we have to choose to send it through the connection tracker. So there's an explicit action. And so you're right. So what happens is that when we receive the packet, we have the SKB, we send it through the connection tracker, and then it goes, and then the SKB's connection tracking bits get set. Right. And so then when we hit the recirculation, now what we do is we look at the SKB and then we see if those bits are set, and then we populate them in the OVS for OVS to look at for the kernel table.
But once your flow is installed, then it's not recirculated, right?
No, you have to keep sending it through the connection tracker,
right,
because otherwise you won't know the state of it.
Is that what you're referring to as recirculation? Just sending it to connection tracker and SKB being marked?
No, not necessarily. So they're actually sort of separate. So So in the first rule, we're actually not recirculating the packet, but we need to send it to the connection tracker so that the connection tracker knows about that, whether the state of the connection, so it knows that it was established already, or was established from port 1. But then you need to keep feeding the traffic, then for and so then we're not going to recirculate in that case, but the SKB bits will be marked, but we just don't look at the packet again because we just forwarded it out. If it came in on port 2, then because we want to enforce policy based on those connection tracking bits, we have to recirculate the packet because the second time through now those bits will be set.
Just another one.
Yeah.
So when we use this contract with OVS, this is in lieu of IP tables with QBR? Or with the bridge?
Yeah, it's an alternative to using the bridge plus IP tables.
Okay.
I think Madhu had a question as well.
I think we're fine because we started this one early, so I think we're good, right?
For this state, right, so we can still use the TCP flag match today.
Yes.
Say, SYN, if it is coming from port 2, just drop all the time, right?
Sorry?
If it is a TCP SYN, drop all the time, right? That
Yeah,
way we can do exactly the same that is done here, isn't it? True?
If we just match the TCP flags?
Yeah, TCP SYN, drop from port 2.
Right. So the problem, well, one, that's only going to work with TCP. It won't work with UDP. You don't get the related flows. And also, it's not really great security because let's say that if you had a system that was being firewalled, you can send packets to to those ports, and then you can do probing to see what services are available by sending an ACK in and then looking at the responses. So it works. It's just not. It's not really a firewall. So, but that is actually how most hardware switches. That's how they implement their firewall rules. When you write an ACL, because they're stateless, they just look at the flags. But this is, so that you can still do it that way if that's good enough for you, and that the performance will be strictly better than running through the connection tracker. But this is a better firewall.
Yes, two questions. One was when the flows get pushed down. I think you're following the same aging policy, I guess, for both kinds, like the flows which are done through contract versus non-contract.
Okay.
Are they going to be aged out at the same time? Like, meaning the stateful rules
Yes.
that gets put in, but they still are subject to getting aged out, right?
Yes.
Okay. Now the second question, going back to what she was saying, the recirculate flag. So when port 1 has established the connection, is it hard to put the reverse, the open flow for reverse direction also, keep them in sync?
So you're saying that...
so that to avoid the recirculation when the packet is coming from port 2.
So were you talking about in this learn example, like versus sending it up to user space with the learn action? So the problem with that is that the performance is so much slower because every new connection is going to require being sent up to user space, and the reply is going to go up to user space, and that kills performance. The nice thing about this is everything stays in the kernel. Once those caches heat up, then everything stays in the kernel, and then all of the processing stays there. We don't have to do that miss up into user space.
No, I was talking about to avoiding the recirculation, right?
Okay.
From port 2 coming back. So when port 1 hits, the first time that there is a connection being established from port 1 to port 2. So
you're saying that
with a SYN, and then you obviously know there's going to be all expected responses with ACK bit set from port 2. You can allow that. So you can go and proactively create an open flow rule, right?
Yeah, I mean, I guess we could do that. It wouldn't you wouldn't get some of the benefits from like ALGs, so you wouldn't be able to punch holes for related flows, for example. The TCP window enforcement wouldn't happen. I mean, I guess we could do something like that. I just don't know if it would. You would end up having to have the kernel be able to insert new flows into the kernel, and that's not currently supported because the user space will be confused because it's going to start seeing flows that come in. So I think that I don't think that there's that running it through the connection tracker. I don't think we'll have too much of a performance hit, and I think that overall you end up with something that's better.
So let me clarify one thing. So you were saying the reason IP table, the performance is worse is because the OVS is processing the packet in the kernel space.
So the reason that the performance is better on OVS is because of the way that we're doing flow caching. So what happens with OVS is that the first packet comes in and it misses, and so it gets sent up to user space. And you have this very complicated, possibly hundreds of thousands of open flow rules, and we figure out what to do with the packet. And then we create a cache entry that says, if the packet looks like this, then these are the set of actions that you want to do. So we kind of take a hit to figure out what to do with the packet early on, but then but once that the flow gets established in the kernel, the performance is much better. So with sorry, I lost my train of thought there. So if it's, sorry, we lost my train of thought. Oh yeah, and so then with IP, yeah, thank you, sorry. So with IP tables, the way that it's written is that there's a linear table that, so when a packet comes in, it looks at each of the addresses to decide what to do with the packet. So you hit that, you have the same performance hit. And like I said, these numbers are sort of worst case for IP tables. So if, for example, the packet, the flow that matched was the first one, the performance would have been like you only had one entry. But when you have 1,000, it's going to be based on where that entry is.
I think we should state at this point that IP tables is going to change into a model called NF tables, which is similar to what OVS is doing, where it will no longer be a linear list of rules, but actually a state machine that can be bytecode programmed. So it can be optimized in a very similar way than OVS has been implemented right now.
Okay, so the design goals when we came up with this, and this is related not just to the connection tracking, but also for any of the other stateful services that we're adding, is that we want to keep the performance in mind. So we don't want we don't want to be sending packets up to user space to do these stateful services because the performance will just drop through the floor. And then also the API needs to have a lot of considerations. So OVS and OpenFlow have traditionally been flow-based and stateless, and without completely changing the model for how the switch is programmed, we need to come up with APIs that, as much as possible, sort of make things look stateless. So even though we're using a stateful service, the descriptions look from OVS or from the programmer's perspective as being stateless. And while all of these services that we're talking about right now are Linux specific because we're using the existing modules within the kernel, we don't want the API to be Linux specific. So we try to come up with something that's more general. And so as Thomas and Frank will be talking about, we're also looking at adding support for NAT, load balancing, and DPI. So we're planning on shipping this with OVS 2.4. The natural first question is, when's OVS 2.4 going to ship? And not sure exactly. Probably, I was hoping it was going to be the end of the year, but based on QA resources and just the timing of everything that we've got to put in, it's probably going to be sometime in the first quarter of 2015, probably, hopefully in the earlier side of that. And so in addition to what we currently have available, we'll also have support for ConMark, IP fragment reassembly, and this is sort of a technical detail, but we are, right now, if you're programming flows from the controller's perspective, when you send something to the kernel, or from OVS's perspective, when you send something to the kernel, you break the pipeline. So things like metadata aren't available when you send it, once you send something through the kernel. And what we're going to do is we're going to hide the fact that we're breaking that so that you can write your flows how I showed earlier, where you send it to the connection tracker and then you recirculate it. And then when it recirculates back, all of the metadata is repopulated. And so it looks as if you were just sort of running the traffic through and there wasn't any sort of break where it was going through the kernel. And so the code is available right now. I have it on my personal GitHub account, and so you can, if you want to take a look at it, it's available there, and the work will be going in there. And so the IP fragment code is probably the next thing that will go in, and so we hopefully in the next couple weeks that will be added. So Thomas is going to go into the stateful NAT.
Thanks, Justin. Yeah, so given we have connection tracking, this allows us to leverage a lot of NAT filter features that already exist in the kernel. And one of them that is very interesting to OVS is stateful NAT. Right? OVS can do NAT, but it's coupled to how flows are set up. You cannot do NAT while keeping state. For example, it would not be possible right now with OVS to do NAT at the same time, do any kind of port mapping. So that's what I've been focusing on over the last couple of weeks and months, is to add stateful NAT to OVS, leveraging the code base or the connection tracking feature that is being added. It will be able to do both source and destination NAT. It will, as I said, leverage the connection tracking, the connection tracking work. It will leverage the NAT filter work, which means we get all the features that NAT filter has in terms of NAT for free. So it will be able to do FTP. It will be able to do stuff like layer 7 IRC parsing. It will be able to support IPv6, IPv4. So pretty much we're getting a big piece of code for free. On top of that, it's able to map a single IP address or a set of IP addresses to a range of IP addresses and a range of ports. So we can essentially masquerade a massive amount of private IPs to a single public IP address or to a small number of public IP addresses. It supports multiple mapping modes. Mapping modes is the algorithm that is used to select the source port when you do the map. It supports the mode persistent, which means it's a static mapping. This means that the mapping that is performed will always be the same, even across reboots. There's a hash-based mechanism, which essentially takes the source and destination IP address, the destination ports, some secret, and pushes that into an MD5 hash and generates a new port. Or you can have a fully randomized port mapping that will be slow, obviously, because it's using a true random number. So how does this work? Very similar to the connection tracking workflow, packet comes into the OVS flow table, and you would have a connection tracking action, which would send it to the contractor to assign the connection tracking state with the packet. So the connection tracker will either create or update the entry in the connection tracking table. That connection tracking entry will be leveraged by the NAT filter NAT code. It will store the mapping in that connection tracking entry. So that we can leverage from the flow table. So the next action would be the NAT action with all the proper NAT configuration, and it will pull in the configuration as needed. And then you can recirculate as needed if you want to match on the connection state as well. This is an example, and I want to emphasize that this is work in progress. It's essentially not that simple to model NAT in an OpenFlow world, because OpenFlow has not specifically been designed to capture stateful aspects. The way it's being done right now is that you would have a first flow which has a connection tracking entry in a specific zone. You would have a NAT action. In this case, it is source-based NATing. You would map it to a /24 IP range, and you would use a hash-based algorithm. Then on the second port, which would be the reverse direction, we track or we match that the packet has not gone through the connection tracker yet, and then we feed it into the connection tracker, recirculate, and if it's an established connection, meaning that we know about its state, we'll feed it into the NAT code again and do the reverse translation. If it's a new connection, we will actually drop it. So this will be a typical firewall situation where you have incoming packets, you NAT them, and you reverse NAT all known connections. But this is just a start, right? We can do much more with having connection state. We can do a lot more. And this model came out of a discussion that was initially started by Frank from Cosmos. they want to integrate DPI into OVS, which is awesome. But essentially, as Justin mentioned, we need to maintain current performance assumptions and performance expectations. So we cannot simply run a DPI engine on every single packet that comes in. So how can we leverage connection tracking work and integrate DPI or other layer 7 services with it? And one piece of code that we can reuse is something called NFQ. NFQ stands for Net Filter Queue, and it's essentially a mechanism to queue packets from the kernel into user space. It's memory mapped based, so it's pretty fast. It's multi-queue, so you can have one queue per core, or you can have multiple applications running on each queue. So what I'm proposing and what I will be working on is a new action which is called NFQ, which essentially enables the OVS data path to inject packets from the OVS data path into an NFQ and send it to user space. So this would be packet comes in, flow table, and you have an NFQ action that sends it to net filter, net link layer, NFQ up to the application running in user space. The user space application can look at the packet and it can send back a so-called verdict. That verdict can be, it can accept the packet, meaning that it should continue processing it. It can drop it, or it can accept it and associate a so-called packet mark. This is a mark that OVS can already match on. So essentially, when the application returns the verdict, follows through with this mark, we can recirculate and mark and match on that mark. A secondary option is to have the application use this user space API for the connection tracking entries and modify the connection tracking entry. So it could match on, it can filter on packets, decide on some verdict, and update the verdict in the connection tracking entry. And then other packets flowing through the OVS data path, matching or being mapped to the same connection tracking entry, can leverage and use these marks. So essentially, this will allow for both modes. We can have a completely synchronous mode where the packet is being sent to user space, and the OVS data path waits for the verdict. And when it gets the verdict, we re-inject. Essentially, this is a little bit different from recirculation. Recirculation would be we map it back into the flow table. Reinjection would be we actually send it back to the net IFRX function, which is the function when a packet comes in from the NIC or from another virtual device. That's where packets land in the actual Linux kernel. So we can reinject it back. We can actually, it might end up in the OVS data path again, or it might end up somewhere else. So we can reinject back into the kernel. Or we can have a completely async model where packets are being fed to user space. They do something based on that, but we just continue processing with the packet and leave the classification run in parallel, and maybe after 10 packets or so, the actual classification happened, and after that, the flow will be handled based on the external communication. Yeah, I think that's pretty much what I mentioned already. In terms of required modification on the net filter side, what is missing is net filter is currently L3 based. There is a bridge tables, which is the L2 version of net filter, but does not have any NFQ hooks at this point. So what would be needed is a reinjection function for the NF product bridge family. And on the OVS side, we would need a new action, NFQ, a new Linux data path action. Obviously, just like the contractor or the NAT action, this would be Linux data path specific and would not be supported in a user space only data path. That's what I had. If you have any questions, shoot. Yeah.
Thank you. Questions for both of you. Once you've moved the statefulness into the kernel, have you thought on what happens in terms of state synchronization and state move when the VM moves? That's the first question. The second question is, I'm interested to find out what your OVS performance is when VM addressing moves from IPv4 to IPv6. I'd like to get some feedback on that as well.
I can answer the first question for sure.
I brought up that drawing. That might help just with the user space netlink API.
Yeah. So there's two answers. One answer is that the kernel itself does not care about state synchronization to other machines. But this is code that actually exists. So there is code outside of the kernel that can take the connection tracking state and migrate and synchronize it to another machine. That is something that a lot of users are already using on the Linux side because they have distributed firewalls or distributed load balancers, and they rely on the state being synchronized between multiple machines. For example, a lot of IPVS use cases are driven by that.
And so that's that user space netlink API. So there are things like contract D, and that runs in user space, and it synchronizes the state between two different boxes. And so that's used through netlink API from user space so there are utilities that already do that, and you can leverage that because we're using the standard Linux kernel facilities.
And it would be the responsibility of the SDN control to make sure that all the switches or all the virtual switches have corresponding rules, obviously.
Yeah, I have a question here. So do these changes bias deployments toward a host-based deployment versus a switch-based or hardware-based deployment? Seems likely that there's an implicit assumption that there's a host underneath this versus a top-of-rack switch or some other OVS alternative.
Well, I don't want to speak for anybody else, but it's definitely in my interest to move more intelligence onto the host. And I think the features we're talking about here are very interesting for the host in particular. I mean, if you look at NAT and connection tracking, that's essentially what an OpenStack deployment needs. And currently they rely on models such as TCP flag matching, which as Justin pointed out and explained very well, that it's from a feature perspective and from a security perspective, is not on the same level as what this can provide.
And in terms of going for this is what goes back to where I was mentioning that it shouldn't be Linux specific. So I guess if you're talking about someone who has a switch ASIC that is running on top of Linux, if they make use of the contract facility and then they copy the state appropriately down to their switch, it'll just work. But it's going to be up to the switch vendors to support the contract. And if they wanted to use something that was not based on Linux, once again, they could just implement their own contract function because we've tried to write this in such a way that it's generic, and then they would just have to do all of the wiring to make it so that it works when the contract function calls that it calls their hardware appropriately.
What I would like to say to this as well is that although there is an OpenFlow action designed at this point, it's a vendor extension, and I would be very interested to have feedback on how we can model this to make it work outside of the software case as well.
All right, let's thank our speakers.